In this section, we are going to talk about the derivatives of exponential and logarithmic functions. Okay. For the first two, we're going to look at just the basic functions of e to the x and natural log of x. And for these, we just have to remember some basic properties about those functions to determine their derivatives. And then we'll look at some of the other properties for other exponentials and other logarithms. Okay? So let's consider the function f of x equals e to the x. Okay? So if we want to take the derivative of this, again going back to our limit definition, limit as h goes to 0 of e to the x plus h minus e to the x over h. We can use our exponential properties to rewrite e to the x plus h. So that becomes e to the x times e to the h. And then we can factor out the e to the x term, which leaves us with e to the h minus 1 over h. And again, because the e to the x term doesn't have an h inside of it, we can treat it like a constant and move it out front of the function. And so we get this expression here. Now, at first look, if we take the limit as h goes to 0, it looks like we're getting 1 minus 1 over 0, or 0 over 0, something indeterminate. But taking a closer look, we can see that as h goes to 0, e to the h is going to approach 0 much faster than h. And so this piece actually does in fact go to 1. So this will be e to the x times essentially 1, which tells us that the derivative with respect to x of e to the x is just e to the x. Okay? This is one of the nicest functions we are going to deal with in this course. Okay. So let's go over here and take a look at the natural log function. Okay. So let's consider ln of x. So the natural log of x, which again we think of as the inverse of our e. So again, using the limit definition, ln of x plus h minus ln of x all over h. Again, we can use some logarithm properties, which says the subtraction of two logarithms is the division of their arguments. So we can rewrite it this way. And more importantly, I can pull that 1 over h out front so that I can actually look at that natural log piece a little better. And to do that, what I'm going to do is I'm going to treat 1 over h as 1 over x times x over h. Okay? It doesn't seem like it's really important to do that, but it helps us rewrite our function. So now instead of having a 1 over h, I can think I have this, and by our logarithm properties, coefficients can be brought up to exponents. And I'm not going to take all of it, I'm only going to take the x over h piece. So the 1 over x I'll keep out front, the other part I'll move up to an exponent. And part of the reason I do that is so that I can again isolate the argument of the natural log. 1 over x doesn't have an h in it, so I can move it out front of my limit, and now the limit can come inside to my argument because the natural log of a limit is the same as the limit of a natural log. Okay? If I look at this piece in the brackets here, some of you may or may not recall from pre-calculus that this expression is really important in terms of exponents and logarithms. Excuse me. More importantly, if you think back to some of your exponential properties and look at things like compound interest, this is an expression that you should be vaguely familiar with. If I take the limit as h approaches 0 of 1 over h over x to the x over h, this is the definition of our e, our transcendental number e. So here, this transforms into 1 over x times the natural log of e, which again, if you remember from your basic properties, this is 1 over x times 1. So this tells us the derivative with respect to x of the natural log of x is going to be 1 over x. Now those are the two general derivatives for our basic exponential and our logarithm. And now we're going to look at some properties and expand on this. Okay. So the first property takes our exponential and says, okay, we know e to the x, we know that e to the x, if we take the derivative, is going to be e to the x. But what happens if I have something other than x in the exponent? So if I look at the derivative with respect to x, where I have e to the u, where u is some function of x, what it says is I'm going to apply my chain rule. So we'll get e to the u, but then we'll multiply by the derivative of u with respect to x. Okay. And we'll look at some examples of these. If I look at the derivative with respect to x of the natural log, so as we just found, natural log of x, its derivative is 1 over x. Here, it says derivative of natural log of u is going to be 1 over u times the derivative of u with respect to x. So again, we're applying a chain rule. Now for the next two properties, we're going to be looking at, well, what happens if my base is not e? Okay, so there are other bases out there, especially for our logarithms. In the case of an exponential, we find it's actually not very different. I can treat a to the u as e to the natural log of a to the u. Okay? Which, I don't mean equals there, I do mean parentheses. So if you notice, e to the natural log, those cancel out, so that's still essentially a to the u. But I'm rewriting it this way because now I can use some other properties to simplify this. In particular, the u can come down front. And we already see that the derivative of e to the u is e to the u. So e to the u natural log of a is going to be e to the u natural log of a. But more importantly, because of that derivative of u using the chain rule, we see that we're going to take the derivative of u with respect to x and have a natural log of a in there. In other words, this is going to simplify down to e to the u ln of a times natural log of a du dx. And again, if we put that back into just terms of a, by what we did before here, this is going to be a to the u natural log of a times du dx. So there's our derivative with respect to x of a to the u. Similarly, we have an argument for logarithms of a different base. Okay? So if I'm looking at a log base a, this could be a common log, or it could be a log base 5 or 2 or some other number. Here again, we can start by rewriting it using our change of base property, which says that if I look at a logarithm with a particular base, I can always rewrite it in terms of logarithms. Natural logarithms in particular. We can choose any base, but more particularly we can use our natural log since we know how to take its derivative. So from here, this says, well, natural log of a is just a number. It's a constant. I can move that out front from our basic properties. So this is 1 over the natural log of a times the derivative with respect to x of natural log of u. And from our property 2, we already know derivative of natural log of u is 1 over u du dx. So our derivative with respect to x of log base a of u is going to be 1 over u ln of a times du dx. Okay. These are the 4 exponential and logarithmic properties you'll need to know. Most of the ones we're going to deal with have to involve properties 1 and 2, but there are a few applications, especially when we get into some later chapters, that are going to involve some of these other bases. So you should be aware of how to find the derivatives in both cases. Here we're going to look at some examples of those exponential and logarithmic derivatives. Some of them are going to be in base E, some of them are not. But this will give us just another look at these properties and how they're used. Okay. In the first case here, we're going to look at the natural log of x squared plus 1. So this one is a base E logarithm, but it does have something other than x in the argument, which means we need to apply our chain rule. Okay. So in this case, using our chain rule, we apply the derivative of the natural log first, and then worry about the derivative of the inside. So our natural log of anything, u, says it's going to be 1 over that u times the derivative of u. Okay. So in this case, we'll go ahead and take that derivative, which is just 2x. So our f prime of x looks like 2x over x squared plus 1. Okay. In the next example, here we're looking at an exponential function, again base E, but also where our exponent has something other than x. So again, we need to apply our chain rule. Okay. So here, f of x equals e to the 3x squared plus 2, again, we'll start by applying the exponential property, which says e to the u, the derivative is e to the u, times the derivative of the u. And so here our derivative is going to be a 6x e to the 3x squared plus 2. Now let's look at some different bases. Okay, so now we're looking at both the logarithm and an exponential where the base is no longer e. So in the first example, we have base 3 and we have a 2x minus 1 in the argument. So again, we're going to have to apply the chain rule. So here, g prime of x, again, by our properties, we can think of this as natural log of 2x minus 1 parenthesis over the natural log of 3. So again, that natural log of 3 will come out front. So our derivative looks like natural log of 3, 1 over a 2x minus 1. That's the derivative of the logarithm times the derivative of the argument. Okay. So there's our 1 over u times the 1 over the natural log of the base times the derivative of the argument. Simplifying, our derivative of the argument is just 2. So 2x minus 1 times the natural log of 3. There's our g prime of x. Okay. In the next one, we're looking at a base of 4, an exponential function where the exponent is a 5x minus 3. So again, we'll need to apply the chain rule for the exponent being something other than x, and we'll have to apply our exponential properties for the base being something other than e. Okay. So again, for our chain rule, we apply the exponential property first. So 4 to the u is going to be 4 to the u times the natural log of the base, which is 4. Then we're going to multiply this by the derivative of the exponent. So here, derivative of our exponent is just 5. So we'll have 4 to the 5x minus 3 times 5 ln of 4. There's our g prime of x. Okay. Now notice here in this exponential property, there's not a way to simplify this further. One of the common mistakes that I've seen in the past is students will try to multiply the constants here, and you can't. There's not much more there's not much more that you can do at this stage. This is the answer and as far as you can go. All right, let's look at one other example. So here we have a more complicated chain rule. So we've got the natural log of 3 to the x plus 2 minus a log base 4 of x. And we want to find the derivative of this function. Okay. The derivative here is going to need to be done in kind of some steps. And again, this is where knowing your chain rule really well will help out. Okay. Looking at my function, the main thing I'm looking at is a natural log of a function. I don't care that that function is kind of complicated. It says that when I take my derivative, the derivative of the natural log of u is again just 1 over the u. So there's the first piece. And again, because it's a u in there instead of just x, we need to take the derivative of that inside piece. Okay. So here, this first piece is not going to change. That's just going to get carried along. Taking the derivative of the inside piece, again, we're going to apply both our exponential and logarithmic properties. So 3 to the x plus 2 times the natural log of 3 times the derivative of the argument, or the exponent. So there's our a to the u property, minus, for our log base 4 of x, well, it's going to be 1 over the argument, so 1 over x, times 1 over the natural log of 4, because I'm looking at something other than base e, times 1 for the derivative of the argument, which in this case is x. So cleaning this up, 3 to the x plus 2, natural log of 3, minus 1 over x ln of 4, all over 3 to the x plus 2, minus log base 4 of x. Last thing to do is get that common denominator, so we get rid of the complex fraction. So we'll multiply by x ln of 4. There's our h prime of x. And I wrote that wrong. I apologize. That should be x ln of 3 ln of 4. Which, if you think about your logarithm properties, can be rewritten even better. No, I can't. That's it. I'm going to add parentheses there to clean that up a little bit. So there would be our solution. Again, not pretty, but we started with a fairly complicated problem. So there's an example of your exponentials, your logarithms playing into your chain rules and some of your other properties.